Okay. Well, as you've probably guessed from the title, this is going to be a talk about entropy. So the title is all about entropy. How many angels can sit on the head of a black hole? Entropy first appeared in the Industrial Revolution as an apparent violation of the law of conservation of energy. You put in some energy and you didn't get out as much work as you thought you put in. It was sort of mysterious, but one of the things you learned about it was it seemed to be extensive in the volume of the system that you were working with. The real fundamental breakthrough in entropy came with the work of Ludwig Boltzmann, who made this crazy hypothesis that matter was made up of tiny little things called molecules, and that entropy had something to do with the number of states, more precisely the logarithm of the number of states of those molecules. Now, he was working with classical mechanics where the number of states is not so well defined. He related it to the volume of phase space of the molecules. In quantum mechanics, we can do a little bit better than that because in finite volume, the number of states is actually discrete, so we can actually count them. And again, the entropy in standard textbook quantum mechanics comes out to be extensive in the volume. In modern days, when I teach quantum field theory, I explain this in the following way. I have a quantum field theory. I usually teach relativistic quantum field theory. So I use units where h bar equals c equals 1. And then everything has dimensions of length or inverse length. So mass has dimensions of inverse length. And I usually talk about quantum field theory with some kind of cutoff at a high mass scale, call it MC. And then if I have a quantum field theory and I've filled up all the states that I can up to the cutoff by dimensional analysis, in a region R, I have MC times R cubed for the logarithm of the number of states or the entropy. So again, the entropy is proportional to the volume. And then a law that we all know for the coarse-grained entropy, the entropy is always increasing. That was something that was discovered phenomenologically, and Boltzmann was able to prove that from the laws of statistical mechanics by doing coarse graining on the equations of motion of statistical mechanics, throwing away higher order correlation functions. It's, of course, entropy exactly in quantum mechanics. If you define it as the von Neumann entropy of a density matrix, it's exactly conserved. But again, if you coarse grain, it increases. Now, in gravitational physics, there seems to be a problem with the concept of entropy that was first pointed out by Jacob Bekenstein. Bekenstein was thinking about entropy in the presence of black holes. And back in those days, this was in the early 1970s, people thought of a black hole as just a unique thing. And he said, well, suppose I have some process and it creates some entropy. And then I take that system where the entropy has been created and I throw it into the black hole. It's then disappeared forever. And the entropy disappeared. And so I've violated in a macroscopic way the second law of thermodynamics. So that better not be true. It must be that the black hole somehow gained entropy. And he noticed that Stephen Hawking had recently proved a theorem about black holes that said that the area of the horizon of black holes always increased with time. And he said, oh boy, that sounds like the second law of thermodynamics. And so he made this hypothesis that somehow the entropy of a black hole had something to do with the area of its horizon. And he even made a little model that kind of explained that. He said, well, suppose I wanted to make a black hole by making it up out of quantum mechanical particles. So I want to make up the mass of the black hole. And I know the relation between the mass and the radius of the black hole. The Schwarzschild radius is just proportional to the mass times Newton's constant. And let's take the lightest particles that I can, namely massless particles, and they have an energy that, if they have a wavelength r, goes like 1 over r. And if I have a black hole of size r, the longest wavelength I can fit into it is of size r. So the lowest energy I can get would be photons or other massless particles of size r. And he also knew that photons have 2 polarization states. So that's like 1 qubit of information. So that's 2 quantum mechanical states. That's an entropy of log 2. And now you just count up how much entropy you've got and count up how much energy you need to make up the mass of the black hole, and it more or less exactly fits. And then the area has precisely the dimensions of Newton's constant. So the area measured in units of Newton's constant could be the entropy. Now that calculation doesn't give you the coefficient out front. Stephen Hawking heard this argument and he said, that sounds like garbage to me. But then, being who he was, he sat down and he did a calculation. He sat down and said, well, suppose we actually somehow made this black hole by starting out with quantum field theory and started putting together a whole bunch of particles that came together and formed the black hole. And let's see what happens in quantum field theory when we form a black hole and look at the final state. And he did a really beautiful, long-winded calculation. You can look it up. It's hard. Nowadays, we all know how to do it. The day that Stephen did it, nobody else could have done it, probably. But it gave a really remarkable result. He found that the spectrum of particles emitted from the black hole was not nothing. You might have said, oh, everything's just going to fall into the black hole, end of story. But no, he found inevitably you end up with a spectrum of particles coming out. And there's a reason for that. And the reason for that is that the black hole closes off a region of space-time inside of its horizon. And that region of space-time is entangled with the exterior, because in quantum field theory, whenever you have a light cone, there's entanglement entropy that comes about because the fields on one side of that light cone don't commute with the fields on the other side of that light cone. And so that non-commutation of operators always gives rise to entanglement. And so the state that you get on the outside is not pure. And so it can't be the vacuum state. And what Hawking showed is, in fact, it's not. And it's a thermal state at a very, very particular temperature. And then if I've got a system that has a particular energy and a particular temperature, I can calculate its entropy. And lo and behold, he got Bekenstein's result, except that he got the coefficient. And it's the area of the black hole horizon divided by 4 times Newton's constant on the nose. He also found a formula for the black hole temperature, which I've written up here. It's 1 over 8 pi times g Newton times the mass of the black hole. The radius of the black hole is the Schwarzschild radius twice Newton's constant times the mass. Now, with Jim Hartle, Hawking then did another calculation that gave a little bit more insight into why black holes have temperature. And he used a principle of quantum mechanics that I hope most of you know. In quantum mechanics, the time evolution operator is e to the minus I times the Hamiltonian times time. The thermal density matrix is e to the minus the Hamiltonian times the inverse temperature. And when you do a thermal average, you're taking a trace of e to the minus h times the inverse temperature times some operator, okay? Now, if I'm taking a trace, that means I'm going around. This is like doing an evolution in inverse temperature for a period of the inverse temperature and then coming back exactly to myself. So I'm periodic in inverse temperature. And what Hartle and Hawking did was they took the metric of the black hole in space-time, and they analytically continued the time coordinate, making it imaginary, like taking time to inverse temperature. And they found that the resulting manifold was singular unless they made a periodic identification exactly by the inverse of the Hawking temperature. And that showed how to compute things in the thermal ensemble given by the black hole, and was a justification for treating the black hole as a thermal state. So we learned from all of this that black holes have entropy. The entropy is proportional to the area over 4 times g Newton. It's not a single thing. It's a huge number of quantum states. We don't know what they are, but they're there. And that they have a temperature that goes along with those quantum states and that entropy. Okay. Now, people started thinking about this, and I'm sure many of you have heard about the so-called information paradox that stems from this. I'm not going to talk about that today. There's a lot to be said about that, but it's not part of what I'm going to be discussing. But there was another point that came up in discussions that mostly never got published. And it was that a lot of people realized, several people told me this in the 1980s, and as a dedicated quantum field theorist, I didn't want to believe it, all right? That they said, you know, if we think hard about black holes, actually, our whole idea from quantum field theory that entropy is proportional to the volume of space must be wrong, okay? Here's how they argued it. Take quantum field theory in a certain volume of space. It says, as I told you, that the entropy in that volume is proportional to the volume. So now let's look at most of those states. So I put in some ultraviolet cutoff on the quantum field theory. One reason you might want to put it there is because quantum gravity has a natural length scale in it. This is one of the reasons that Planck liked Planck's constant, because together with Newton's constant and C, Planck's constant, defines a natural length scale. And so you might imagine that gravity defines a natural cutoff scale for quantum field theory. But it's going to turn out that's a very bad cutoff for this calculation, as we'll see in a minute. But put in some cutoff scale for the quantum field theory. And let's talk about the typical energy of one of those states up near the cutoff that make up most of the entropy according to quantum field theory. And we're just talking about what we think is flat space. Now let's calculate the expectation value of the energy of that state. It's huge. It's equal to the cutoff scale times the entropy of that region. All right? It's the energy density in that region times the size of the region. Now, let's say, oh, wait a minute, we have gravity in the picture. So therefore, we shouldn't be thinking about flat space. We should think about the back reaction of this mass on gravity. And it's going to make a black hole. Well, let's see how big that black hole is. Well, the black hole is much, much bigger than the region R we started with. And now, well, how can we fix that? We can try to put a cutoff that is so low that it will make the black hole smaller than the region. Well, the only way you can do that is as you make the region bigger, you can do the algebra for yourself. As you make the region bigger, you have to take the ultraviolet cutoff on the field theory lower and lower and lower in order to keep the black hole mass below the size of the region. The black hole Schwarzschild radius, which is proportional to its mass. So if I do that, I can then calculate how much quantum field theory entropy I'm actually allowed in that region. And it's not enough to even account for the area on the boundary of that region, which is what I would have expected if there were a black hole in that region. So this suggests that quantum field theory is drastically wrong in its picture of what the typical quantum states are in a region of space-time. Now, how can that be? Because we've done these incredibly precise experiments that test quantum field theory up to 10 to the 16th, 10 to the 17th GeV with enormous precision. You've all seen the fine structure constant and G minus 2 of the electron and the muon, the degree of precision with which those agree with quantum field theory. Well, in 1998, there was a really lovely paper by Andy Cohen, David Kaplan, and Ann Nelson that showed that all of those calculations could be done even if you threw away all of the states that you had to throw away to get rid of this paradox with forming black holes. And I can give you a hand-waving reason for why that's true. When you do an experiment, you've got an apparatus, and that apparatus is traveling along some trajectory in space-time. And you're really only testing quantum field theory along that trajectory. Now, that experiment takes place for a certain period of proper time along the apparatus's trajectory. And during that proper time, in principle, you could have sent out signals and received them back from a very large region of space-time. We're going to call that region the causal diamond of the apparatus. We'll talk about that in a minute. What we usually assume is that quantum field theory is good throughout that causal diamond. But we're not actually testing quantum field theory throughout that causal diamond. And if we tried to do that, if we set up simultaneous experiments everywhere in that region and tried to fill the causal diamonds with experiments that tested G-2 everywhere, we wouldn't succeed because those experiments would be big, massive machines, and the mass of them would come together and collapse the region into a black hole. So this is not what Cohen, Kaplan, and Nelson did. They did real quantum field theory calculations and showed that you could throw out these states and it didn't matter. But this is the intuitive reason why what they did worked. Now, it turns out that there had been even earlier arguments due to Werner Israel and Gerarda 't Hooft. 't Hooft had proposed that one try to understand the entropy of black holes in terms of quantum field theory states right near the horizon of a black hole. And 't Hooft and Israel in the early 1990s tried to explore that hypothesis and ran into trouble. And they were the same kind of back reaction troubles that I've been describing to you here. I won't go into details about that, but in 2013, a whole group of other people started worrying about problems similar to the ones that 't Hooft and Israel ran into that had to do with detailed issues with quantum information, the thinking about the information that supposedly comes out of the black hole when it emits Hawking radiation, and whether it's compatible with the fact that the black hole only has a finite amount of information in it. And this whole idea that the black hole entropy can be understood in terms of quantum field theory applied to the horizon around the black hole just doesn't work. Now, I can't go into the details of those arguments, but it's really been deflated completely by now. So what is most of the stuff in the universe made of if it's not quantum field theory? So now we're going to have to talk about causal diamonds. So if you don't know what a causal diamond is, just wait a second. During that second, you could have sent out signals to some place in space-time and gotten a signal back. And if I look at if you look at the entire region of space-time you could have explored by doing that, that's your causal diamond. If you look at the person sitting a few seats down from you, they have a similar causal diamond. It's not the same as yours, but it's their causal diamond. So every time-like trajectory in space-time over any finite proper time interval has a causal diamond associated with it. And the boundary of that causal diamond is a pair of light cones. It's the backward light cone from the future point of the time interval and the forward light cone of the past point of the time interval. And that's why we call it a diamond, because if we draw a picture and we project that picture on a two-dimensional plane, it looks like a diamond. Okay. So this is a picture of what a diamond projected on 2 dimensions looks like. It's a diamond. And these are the light cones. These are, of course, actually surfaces of rotation. They're 2 spheres. Every point on these cones is really a two-sphere. And then if I look at the past point and the future point, there are a lot of different time-like trajectories that connect those 2 points. But there's one that has maximal proper time, and that's called the geodesic between those 2 points, the time-like geodesic. And that's one of the invariants of this causal diamond. And then there's another geometric invariant of the causal diamond, which is the following. If you start out at the top of the causal diamond, or at the bottom, and you start looking out along the light cone and measure the surface area at any fixed null interval, any fixed light-like interval along the light cone, you'll see an area. That area starts to grow in both directions. Somewhere in the middle, it takes on a maximum. In flat Minkowski space, that maximum is at the time-symmetric point between the two. If the space-time is expanding, it'll be different. It can get quite complicated, but there's always some maximum someplace, and that maximum area is a geometric invariant of the diamond. So in 1995, Theodore Jacobson wrote what I consider to be one of the most important papers in understanding what quantum gravity is all about. He didn't quite say it this way, but effectively made the hypothesis that the basic principle underlying quantum gravity is that given a space-time, for every causal diamond, there's an entropy, where by entropy I mean the expectation value of minus the logarithm of the quantum mechanical density matrix associated with that causal diamond. Okay? There's an entropy equal to the area over 4g Newton. So this was the Bekenstein-Hawking law for black holes. For black holes, the inside of the horizon of the black hole is a causal diamond. Okay? But this is generalizing that statement to an arbitrary causal diamond. And you'll see why this is a good hypothesis to make in just a minute. Because what he showed is that with a couple of extra hypotheses, this hypothesis derives Einstein's equations as the hydrodynamic equations of this hypothesis about entropy. So the way Ted said this was he said, look at locally at the equation dE equals TdS. So we know what S is. We have to understand how to vary S. It turns out variation of area, there's a nice equation that depends just on geometry, doesn't depend on Einstein's equations or anything, that was derived by a fellow named Ray Chowdhury many, many years ago. And in the vicinity of a maximal area surface, that equation simplifies dramatically in a way that I'll show you in a minute. And the E we know how to write in terms of a conserved stress-energy tensor in space-time. And then there was a question of what to take for the temperature. Well, if I have a large causal diamond in space-time, near any point, space-time is approximately flat. And Bill Unruh had showed that if I look at an accelerated trajectory in flat space-time, it sees an effective temperature. And that if that trajectory approaches the light cone, that temperature goes to infinity. So Jacobson hypothesized that he could use that limiting infinite temperature for the trajectory that approached the light cone near this maximal surface, and was able to derive Einstein's equations. Now, this tells you two things. Number one, it tells you you should think of Einstein's equations as the analog of the Navier-Stokes equations. They're the hydrodynamics of quantum gravity. And the other thing it turns out is Jacobson doesn't quite derive Einstein's equations. As we'll see in just a minute, Einstein's equations are tensor equations in space-time. They're equations for a symmetric tensor, or we'll talk about. And he only derives them dotted into an arbitrary light-like vector any place in the space-time. There's one term that he misses in Einstein's equations, and that's the so-called Einstein cosmological constant. Okay? Now, that's a term that quantum field theorists have found problematic for decades, because in quantum field theory, that term appears to have something to do with the ground state energy density, and it always comes out infinite, and it's something that we don't understand. What this derivation tells you is you should not associate that term with an energy density. It doesn't have anything to do with hydrodynamics. The hydrodynamic equations don't depend on the cosmological constant. Now, there are a couple of people who know string theory in the audience here. Those people know about the anti-de Sitter conformal field theory correspondence, where it's absolutely clear that the cosmological constant has nothing to do with the ground state energy density, but is instead an ultraviolet parameter of the theory. So I'm not going to do specialized stuff like that in a colloquium. Okay, let me give you a paraphrase of Jacobson's argument. So basically, near a maximal area surface, the variation of the area, let me vary the causal diamond by changing the endpoints of that trajectory a little bit. So when I'm thinking about the area, what's happening, I have two light-like trajectories that were originally parallel to each other, going in the same direction. Km is the 4-vector in space-time that tells me where they were going. And now those two are going to spread a little bit. And that spread is coming to first order near the maximum just from the local curvature of space-time. If you want to ask what's happening more generally, there are a lot of other complicated terms in Ray-Chowdhury's equation, but right near the maximum, it just comes from what's called the Ricci curvature tensor. So that's the equation for the variation of the area, okay? So that's the variation of the area. Now, usually when we write hydrodynamics, we want to write the variation of the entropy. We're writing it just on this null surface, the boundary of the causal diamond right now. But we'd like to think of it in hydrodynamics as coming from a conserved entropy current that's flowing through all of space-time. Well, there's a unique conserved entropy current whose first term is the Ricci curvature. And it's the so-called Einstein tensor, Rmn minus a half Gmn R, where Gmn is the metric, and R is this combination of the metric and Rmn. This Einstein tensor, set equal to 0, is the vacuum Einstein equation. Okay? So it's the Einstein equation without any energy density. This says that we get the Einstein equation, but only dotted into an arbitrary light-like vector, Km. This should be Km, Kn, and that's what we get. We could have another term here. If we had Gmn times a constant, that would be another term in the Einstein equation, but it wouldn't contribute here because that gives exactly 0. So it doesn't contribute to the entropy current. Okay? So that's, as I said, the argument that the cosmological current is not really part of hydrodynamics. Now I'm going to make another statement. There's another hypothesis that was made in 1998 and 1999 by Fischler and Susskind and Busso, which is that this area law is always a maximum of the entropy. So I said this was a law for the entropy, but what is this? When I talk about the entropy, it's the entropy in some of this diamond in some particular state of the system. So this is a state, given the background geometry, in which all the causal diamonds are completely empty. Fischler and Susskind and Busso made the additional hypothesis that area law entropy is always the maximum. So what that means is that if I put some energy density into these causal diamonds, that always decreases the entropy. That's weird. You always think, oh, if I put some energy density into a region, it increases the entropy. Well, I'm going to show you in a little while some evidence that proves that you're wrong. But before I do that, let me ask, since we're talking about the hydrodynamics of what? Let me quickly check how much time I have left. Some more time. So now I want to talk about another paper that was written in 1998. It's actually two different papers written independently by Steve Carlip and by Sergei Solodukin. They considered black holes. In 2021, Catherine Zurich and I rediscovered these papers, and we generalized their argument to general causal diamonds. The difference is, for black holes, the area along the horizon doesn't change as you go along the null surface of the causal diamond. For general causal diamonds, of course, it does change, and there's a maximum. The derivation that these guys gave always works at the maximum. And so the only thing they missed was, for a general causal diamond, you have to be working at the maximum. So what they did was they said, let's think about the black hole, and let's let the area on the horizon fluctuate, but locally, by a different amount at different positions in angle on the horizon, okay? And let's consider that fluctuation to be a function along the null coordinates z and t that are going along the horizon direction. Let's let that factor of the area variation just depend on those coordinates. And let's consider what its stress energy looks like as a function of z and t. And what they found, just using the classical Einstein equations, was that it looked like the stress energy tensor of what's called a conformally invariant field theory in the the two dimensions of Z and T, okay? And that it had what's called a central charge, which an example of a conformally invariant field theory is just a free massless scalar field, all right? And the central charge is kind of just counting the number of free massless scalar fields. So that's a simple way to think about it. And the central charge was proportional to the area of the horizon divided by 4 times g newton, okay? And then using the rules of quantum conformal field theory, so they did a completely classical calculation, but then making the hypothesis that underlying that was a quantum conformal field theory, they calculated the entropy of that system using a formula that had been derived by John Carty for conformal field theory a long, long time ago. And they showed that they reproduced the famous Bekenstein-Hawking area law for every single black hole in every dimension with any angular momentum and charge and whatever you like. Catherine and I generalized their calculation to arbitrary causal diamonds, and we also pointed out that since it's a conformal field theory, it leads to this fluctuation formula for the logarithm of the density matrix. And that was the reason we were interested in it, because Catherine and her collaborator, Eric Verlinde, had proven this fluctuation formula by totally different means for a whole class of other models based on the anti-de Sitter space conformal field theory correspondence. So this was a very, very general derivation of why their result worked and why it was a very general result. Patrick Draper and I recently proved the same thing using a replica trick for de Sitter space. So we believe that this argument really holds water. Okay. Where does this conformal field theory live? For a general causal diamond, the maximal area surface is over here, and the conformal field theory lives in this little sliver called the stretched horizon, either in the past or the future. The past and the future ones are related by time translation, and so they're basically the same theory. One is mapped into the other by the unitary time translation operator. Now, I'm getting a little late, I think. Yeah. So let me skip over some things. Now, let me show you the real reason that I believe that argument that putting something local into an empty causal diamond reduces the entropy. So this is a formula that's been known, I think, for more than 50 years. This is the metric of a Schwarzschild black hole, but in de Sitter space, okay? De Sitter space is the maximally symmetric space-time with positive cosmological constant. And you should be interested in it because it appears to be the space-time towards which our own universe is evolving or will evolve in the asymptotic future, okay? Now, normally, we say that Minkowski space has a vacuum that has 0 entropy. That's what quantum field theory tells us. But de Sitter space has a positive cosmological constant, and it has an empty space solution which was calculated to have a maximal area causal diamond with an area that actually is very large. And so it's got an entropy. And it's an entropy that goes to infinity as I take the limit as the radius goes to infinity and I approach Minkowski space. So this suggests another thing that quantum field theory gets wrong, the idea that the Minkowski space vacuum is a pure state. Okay? Now, when I look at the black hole in de Sitter space, you don't have to even know too much about general relativity to do the calculation that I'm going to tell you to do. The horizon of the black hole is given by zeros of this function over here. And as you can see, solving for those zeros reduces to solving for the zeros of a cubic polynomial. We can all do that. There are two positive zeros. One of them, when I take the Schwarzschild radius parameter to 0, that's the thing that is the Schwarzschild radius of the black hole in flat space, this RS. That one goes to 0. The other one goes to capital R. That's the radius of de Sitter space. Those are the two positive zeros. Well, one went to 0 in the limit I was talking about. Now what happens when I turn on RS a little bit? Well, if you know anything about cubic polynomials, those two positive zeros start to approach each other. Okay? And so that means that the big radius of de Sitter space shrinks as I put a black hole into de Sitter space. And it shrinks by an amount that's proportional to the big radius, which is way larger than the increase in entropy that I get by turning on the black hole. And so there's actually a huge entropy deficit for putting a black hole into de Sitter space. Okay? And if you calculate what that entropy deficit is, it's 2 pi r times m. And so if you ask, what's the probability that I would just fluctuate randomly and make this black hole randomly in empty de Sitter space, it's e to the minus 2 pi r times m. And that looks like a Boltzmann factor with temperature 1 over 2 pi r. Now, long ago, Gary Gibbons and Stephen Hawking did a quantum field theory calculation in de Sitter space, just like the Hartle-Hawking calculation for a black hole, and they showed that de Sitter space has a temperature that's 1 over 2 pi r. And so you can get that temperature from this calculation of the entropy deficit. All right? So this is for me, a proof of the fact that putting localized objects into de Sitter space reduces the entropy by a lot. And by extension, when I take the radius to infinity, that means that somehow localized objects in Minkowski space are also reducing the entropy of causal diamonds that they enter. And so Willy Fischler and I have developed a scattering theory of objects in Minkowski space that's based on this idea, and which says that you should follow the trajectories of objects in Minkowski space by saying that The empty diamonds in Minkowski space are in this very impure high entropy density matrix that an excitation that has a localized thing in it corresponds to suppressing some of the qubits on the boundaries of these causal diamonds, and that you follow the trajectories of that excitation into the bulk by following the path of these suppressed qubits. So this picture is supposed to show you how that works. It's a very clumsy picture. You have a larger causal diamond. There were some suppressed qubits on the larger one that propagate into these suppressed qubits here. Similar thing here. Then the suppressed qubits here propagated out through here, got into this causal diamond. And you can see how pictures like this can sort of mock up Feynman diagrams for particles propagating in space-time. Okay? Now, when you do this, it's really important that the number of qubits you suppress is very small compared to the total number of qubits. If you don't do that, you've pushed your system way out of equilibrium, and what you're going to do is get a very different kind of state than the one you put in. So there are two examples of what can happen. Here's an example of what happens inevitably when you keep on doing this and go into smaller and smaller causal diamonds. This was another attempt to make a picture of this. These red dashes are showing you suppressed qubits. And then when they get into the very tiny causal diamond in the middle, I've suppressed almost all of the qubits in the system, or more than half. And therefore, I've thrown the system completely out of equilibrium. And what comes out will not look like what went in, but the total amount of suppressed qubits has to be the same. Now, that statement, you have to build your Hamiltonian in such a way that that total number of suppressed qubits is approximately conserved. And we can do that. I don't have time to really try to show you the mathematics of that, but that's something that can be worked through. And so this is a picture that looks like two paths of suppressed qubits going in and three coming out. But that's what happens when the place where this non-equilibrium state occurs is a very, very tiny microscopic causal diamond. What happens when it's huge? What happens when it's macroscopically large? Then what happens is I get a very out of equilibrium huge system. It quickly comes back to equilibrium. But from the point of view of an even larger causal diamond, it has a huge entropy. So it's a huge equilibrium system that is a big excitation from the point of view of the vacuum state. This system will then spontaneously spit off little bits of itself because it will go into states where some qubits are suppressed in such a way that they don't interact with the rest. And we've tried to argue that that will reproduce the properties of Hawking radiation. So, well, how much time do I have? I don't think I have enough time to, no. Okay, we have some models based on matrices that actually reproduce the scaling laws of black hole physics based on actual quantum mechanical models where the fundamental variables are matrices with fermionic the matrix elements are little fermionic variables. So we can get a lot of physics that looks a lot like the physics of gravity out of these models. Yeah. Okay. Let me go to my conclusion since I'm running out of time. We don't yet have a complete theory of quantum gravity, far from it. There are a lot of things that we don't know how to do yet. But theoretical arguments based on thermodynamics and very simple quantum mechanical models and the properties of black holes definitely suggest that our traditional notion that entropy is extensive in the volume is just wrong. And the idea that localized excitations increase the entropy is also wrong. The correct theory, we believe, is holographic in nature. The basic variables live on the boundaries of causal diamonds. The localized excitations, all of us in this room, everything we see around us, correspond to suppression of fluctuating qubits on faraway causal diamonds. I'm sorry if you don't feel like that's what you are, but that's what these models would say that you are. And what propagates in the bulk are these constraints. There really are actual mathematical models that embody these pictures that I tried to show you. In anti-de Sitter space, the whole story has to be changed a little bit. That's relevant only for those of you who are string theorists. Let me end by saying that this is all not just pie-in-the-sky theory. We have built on the basis of this a model of inflationary cosmology. We think it makes more sense than normal inflationary cosmology. Normal inflationary cosmology has what are called trans-Planckian problems. The way I like to say that is that in normal inflationary cosmology, everything we see in the universe is hypothesized to have originated with field theory degrees of freedom in a little causal diamond that was about 10 to the minus 27 centimeters big, okay? And that violates these bounds on how much entropy can be in such a region. Our model doesn't do that. Our model fits the data on the cosmic microwave background as well as standard inflationary models do. It makes predictions for non-Gaussianities and for tensor modes that are different from standard inflationary models, but I'm afraid I'm not going to live long enough to see those predictions tested. We are currently working on a slight variation of the model that may be able to explain the properties of the early galaxies and little red dots that have been observed in the James Webb Space Telescope. Finally, this is not mostly my work, but the work of Catherine Zurich and her collaborators, who I urge you to invite to give a colloquium on her work on interferometer experiments that are based on similar holographic ideas about how quantum gravity works. Those experiments, if they ever get done, are extremely exciting and might actually show us real evidence that our ideas about quantum field theory and quantum gravity are really quite wrong and have to be modified in the ways that I've indicated today. Thank you.